My name is Engineer Bonna Namde. Today we're going to look at shear forces and bending moments. So we will start with an illustration. We have a beam. Let's draw a beam. I have a beam which is supported at point A. This is point A, and we'll have point B. It's simply supported at point A and B, and let's call this point A and C. Then it has a concentrated load which is eccentrically placed. It's not at the center. So let's say this beam, and this is where the load is concentrated. Let's call this A, point A. This point A, this is point B, and this is point C. This is point, let's call this B, and then call this very one C, point C. So these are point C. So this beam is of 5 meter in span, 5 meter length. Then here from A to B is 2 meters. Let's take 2 meters, and from B to C is 3 meters. So we have to find the reactions. That's the first thing to do. That's A and C. So, and this load is 10 kilonewton in size. So since if this load is at the center, we can easily find the reaction by dividing the load by 2, but it is not at the center. So reaction A and reaction C cannot be equal. So all we need to do here is to find the reaction. To do that, we need to first of all note that total load is equal to RA, reaction at A, plus reaction at C. So the first thing we need to do is to take moment about A to find reaction B. So what do we do? By reaction C, not A, reaction C, not B. So what we'll do here is we take moment about A. So this multiplied by its lever arm becomes RC multiplied by its lever arm from A, which is 5 meters. Then we subtract by the load multiplied by this lever arm about A, which is 10 times 2. This will be equal to 0. So moving this down to the right hand side, we have 5 reaction C is equal to this crossing to this side, we change to plus, so it turns to 20. So we divide both sides by 5. Our reaction C will be equal to 4 kilonewton. So, but we know that total load, which is 10, said that earlier here, is equal to reaction A plus reaction C. So our reaction A will be equal to 10. When we take this to the other side, it will change to minus reaction C, and this will be equal to 10 minus our reaction C is 4. So this will be equal to 6 kilonewton. So our reaction A is equal to 6 kilonewton. 6 kilonewton. Then alternatively, we can also find reaction A. Use alternatively, what do we do? Our reaction here we can take moment about C to do that. So take moment about C. So it will be reaction A times its lever arm from C, which is 5 meters. So alternatively, we can find reaction A by taking moment about point C or about C. So we have, this will be reaction A multiplied by E's perpendicular distance, which is 5 reaction A, minus, we have the load, which is pointing downward by E's lever arm or perpendicular distance, which is 3 meters. So we have 10 times 3 is equal to 0. So if we take this to the other side, it will change to 5 reaction A will be equal to, this minus will change to plus. So we have 30 is equal to 30. So we divide this by 5, divide by 5, this will cancel. So we have reaction A is equal to 6 kilonewton. So now the next thing we need to do, we've been able to find A by using this approach or using this alternative method. So the next thing we need to do now is to draw the shear force diagram. So let's look at the shear force diagram. Here it's a shear force diagram. So to start with that, we draw a line. Let's pick a line. A line of 5 meters. Let's take it downward a bit. A line of 5 meters. So here we know that we have, if we want to calibrate the line, we know that here will be A for 1 meters, so 2 meters. We can always calibrate it, or if we want to use our free hand, what we now need to do is we consider that this is from point A, this is point A, and this is point C. So what we need to do next is to, this load is acting upward, so we have a line going upward. Let's say from here we have a total distance of, from here vertically we are looking at, let's take about interval between 1 0 5 0, this is 0, this is 5, this is 10. So this side we take 1 2 3 4 and 5. So what we need to do here is, our load is going upward at a magnitude of 6 kilonewton. So this is 5. So 6 should be slightly here at this point. So let's mark it as our 6 kilonewton. This point is our 6 kilonewton here. So what we need to do is to draw a line. We draw our line from here, 6 kilonewton. So we'll now move towards the right. This is a concentrated load, so we'll have a straight line. The shear force diagram is a straight line. Or we'll consider the points at, as this load moves down to the left, to the right. When we'll get to the point where we have, which is 2 kilonewton, where we have the 10 kilonewton, we will subtract. We have 6 here. We've gone 6. Let's write it down. Let's say this is 6 and this is 10, and here is 5, here is 0. So here we have 6 moving this way towards the right to meet this load going down. So difference between 6 and 10 go down. Let's use a straight line. So we'll go down here by, difference between 6 and 10 is 4. So we stop at 4, because as we have positive 10, 0 to 10, we are also supposed to have positive or negative 10 also from here. Also have negative 10. There should be 5, and this is 10. So we can also name this 5, and this is our 10. This is minus, this is minus. So here we move down up to 4 kilonewton negative. As we move up to 4 kilonewton, we continue to move. Let's still use a straight line to draw. So we'll continue to move from here until we get to the end where we'll have C. We don't have any other upward or downward force until. So for our shear force, At any point, just as we've drawn here, our shear force is the difference between upward forces and the downward, any upward force and the downward force. So it's a difference between upward forces and downward forces. So here we have, if we're moving from the right, we know that the first force that we have here is reaction A. Is reaction A. So our reaction A is equal to 6 kilonewton. 6 kilonewton. So when we move here, we have 6 kilonewton. So when we get to point B, it will be 6 minus 10 kilonewton, and this will be equal to minus 4 kilonewton. So at point B, our shear force is equal to minus 4 kilonewton. So this minus 4 is still the amount of shear force we'll have from point B up to point C. So at point C, shear force will be equal to minus 4 kilonewton. So the next thing we need to look at is the bending moment expression and its diagram. So let's do that of bending moment. Right, is expression. Bending moment is, as we consider along the beam, it is the difference between, here we have, because at this point, we consider at this point at arrow A, the moment is 0, doesn't have a perpendicular distance. So we are looking for the bending moment at A, point A, BM is equal to 0. So when we move down, if we move to 1 meters, at 1 meter, it will be equal to, we now have the reaction A times 1 meter, and this will be equal to 6 times 1, which is 6 kilonewton meter. At 2 meters, which is our point where we have this, it is going to be equal to 6, which is reaction A, times 2 meters, which will be equal to 12. This will be equal to 12 kilonewton meter. 12 kilonewton meters. So at 3 meters away from B, at 3 meters is going to be equal to reaction A, or 6 kilonewton, times 3 minus, because we have this load by each lever arm, which is, this lever arm at 3 meters will be 1 meter, minus 10 times 1. This will be equal to 6 times 3 minus 10, and this will be equal to 18 minus 10. This will be equal to 8 kilonewton meter. At 4 meters, here, at 4 meters, if we get to this point, the lever arm between here and here will be 2 meters. So it is going to be 6, or reaction A, times, at 4 meters it will be 4 minus 10 multiplied by its own lever arm, which is 2 meters, times 2 meters. This will be equal to, here we have 24 minus 20, and this is equal to 4 kilonewton meter. So at 5 meters, this will be equal to, here we have, the lever arm will shift to 3 meters. Instead of 2 meters, it will shift to 3 meters. So what we have here is reaction A, which is 6, times lever arm, which is 5, minus 10 times 3. So this is equal to, so we draw our bending moment here we have, let's put these values down. We have, let's call this 0, let's call this 10, and this is 20, and this is 30, positive. Then this is 10, this is 20, and this is 30, negative. This is minus. Okay, so here let's call this 1 meter, and this is 2, this is 3 meters, and this is 4, this is 5 meters. So what do we need to do? To consider at point A it is 0, at 1 meter it is 6 kilonewton. 6 kilonewton. So go here, we have 10, so here should be 6. We just shed something, just tick here as 6. This is our 6 kilonewton. Let me use another color. So we use here 6. We say here is our 0.6 kilonewton. Then here we have, we just mark it as X. So the next one we have is at 2 meters. We have a total of 12 kilonewton positive. After 10, we should have 12 somewhere here. At 3 meters, we have 8 kilonewton. So here we have 8, going down a bit, because 8 is lesser than 10. So we also mark 8. Then at 4 meters, we have 4. So 4 is also lesser than this. So we should have 4 here, 4 meters. At 5, we have 0. So here, remember at A, which is at the first point, we had 0 also. So all we need to do is to join it. So we join this. As we join this, so this is our bending moment diagram. So we'll call this our bending moment diagram for this problem. So this is bending moment diagram. So we've been able to draw the shear force and the bending moment diagram for this